So today we will continue our discussion on measurable functions, and today we are going to basically establish some results, some very important results rather, about sequence of functions and then their limits. Okay, so we are going to talk about various kind of limits for a given sequence of measurable functions and try to establish certain results. And the idea is because we will have to consider the notion of integration, and that process requires a lot of approximations of general functions by some known class of functions. So we will need to understand the idea of limit for a given sequence of measurable functions. Okay, so in this lecture we start that, but before getting into this, I will try to also introduce an abstract setting for the measurable functions and for the measurable sets and in general. So right now we have been always talking about till now uh, subsets of R and Lebesgue measurable subsets of R, correct? But this notion of measurable sets can be extended to the general setting, namely that you don't have to always work with subsets of R. You can take an abstract space. So I will introduce this, and uh, all these properties that we have proved, most of them they can be proved in general also, but in this course we will always restrict ourselves to Lebesgue measurable setting, because that is more concrete, and you can work out a lot of concrete examples in this particular case. Okay, but keep in mind that there is a general concept, and that is what I will just briefly introduce. And many of these results which we are going to discuss or we have discussed, they can be put in the abstract setting of a general set, okay, or measure space that I will define. All right, so this is the first part is just going to be sort of a repetition. So what you do is uh, you consider a set X, non-empty set X, and take a sigma algebra on this. So this S denotes the sigma algebra, and then we say that this pair, this ordered pair, is a measurable space. Okay, so imagine like X was real line and this S was your sigma algebra of all measurable sets that we had defined. Okay, but this process you can consider any set and consider a sigma algebra on it, and consider this pair X and S. We always refer to this thing as a measurable space. Okay, the measurable space, because we can measure in some sense these subsets of this. Okay, so this is what is called a measurable space. As I have been telling you, that these two examples we have discussed, so we know them. So this is the one which often we are going to work with, and this is very close to the second one, the Borel sigma algebra. Okay, so these things you can keep in mind, but you can try to consider some more examples. Okay, so for example, I will ask you to, so consider X equal to this set of integers and try to consider a non-trivial sigma algebra on this. Okay, and then that will also give you uh, a measurable space. Okay, and then once I have a measurable space, with respect to that I can define measurable functions. Okay, so let us take a measurable space, that means X is a set and S is a sigma algebra on it, and then you consider functions from this set X to the extended real values, and then it's the same definition. All you need to worry about that, look at the sets of points where fx is bigger than a. If this guy is measurable, so what is the meaning of measurable here? That this should be inside the sigma algebra that you have started with. Okay, so in the case of R, this was just the Lebesgue measurable set, a collection of it, Lebesgue measurable sets. So this, if you can verify that for every possible number a, this set is in the sigma algebra that you have started with, then you refer to these functions, or these functions are called measurable functions. Okay, so this is precisely the same definition but put in the abstract setting. Okay, So this is something you need I mean, you can always, and now you look into the properties which we have proved for Lebesgue measurable function. You can try to extend them to this situation. Okay, this is fairly easy, just imitating the same thing. It can be done. Okay, yeah, so this is what I have written in the remark. And now this is just the the sigma algebra. Now we can also consider a measure on this. Okay, so right now I'm not saying anything about, I mean, whether we can always consider a measure or not. But suppose we have a measurable space, and on this collection of set, or like on this sigma algebra, if we can define a function which satisfies these two properties. So this mu is a function which is defined on the sigma algebra to non-negative extended real numbers, such that the empty set is assigned 0, and this is countably additive. Okay, so this is the property. If you remember, this was the one of the most important property. So if these two properties are satisfied by a function defined on the sigma algebra, then this mu is called a measure on the given measurable space. Okay, and this gives rise to, yeah, so this has to be, this is countably additive. That means these guys were coming from S, and they were mutually disjoint. So this is so these are the two properties, and the notion of measure can be defined in general or in abstract measurable space. Okay, as I was telling you, like, so this is your measurable space, but if you have a measure on it, then we get this triplet X, and then the sigma algebra on it, and then the measure on the sigma algebra. So this is called a measure space. Okay, because this is the space where you can measure the size of the sets from the sigma algebra. Okay, so this is what and then attached to it there are few more definitions. For example, if your X, because we are working with a sigma algebra on X, so this S will always contain X, the full space. So if the measure of the full space is finite, then this measure space is called a finite measure space. For example, I mean, what you can do is you can consider the consider, let's say, closed interval 0 1 as a subset of R. Okay, and then you can take Lebesgue measurable subsets of 0 1 that will also form a sigma algebra inside 0 1. And then we know that the Lebesgue measure of 0 to 1 is finite, so that is like a finite measure space. So from R you can always restrict things to basically a finite measure space. You just take a set which is a finite measure, and then you can get a finite measure space. Okay, and the second definition in this direction is that if I have a measure space, and if I can express this measure space X as a countable union of sets such that each of these set has got finite measure, then this is called a sigma finite measure space. Okay, sigma because this can be expressed as a countable union of finite. Okay, so for example, the real line, I mean, you can write real line as union of minus n to n, for example, and minus n to n, that is your En, and each of these set will have finite measure, but R can be expressed as a countable union. Okay, so this for example, R is an example with the Lebesgue measurable sets, and the Lebesgue measure, that is an example of sigma finite measure space. Okay, so these are some technical terms which I will not use them right now, but later on in the course we will prove certain results where we will require at some place this sigma finiteness, okay, of this space. So this it's better to keep these definitions in mind. Okay, so again, I mean, examples I am always going to consider for this particular reason, that that you understand this particular example of Lebesgue measurable space or Lebesgue measure uh, in a really a good way, so that, and then rest things can be worked out. Okay, so this is why I am always keeping the example of just the Lebesgue measure. Okay, this is very concrete, and this is like you can develop an intuition that how things are going to work out over here. Okay, so now let's come back to as I said, that today we are going to basically discuss the notion of convergence and the limits. So this is what the main part I wanted to discuss today. So I will just start the definitions of point-wise convergence, which has been given earlier also, but let us just briefly recall. So what we are going to do is we are going to consider a sequence of functions. And why are we going to do this? Because we need to uh, we will have to approximate general functions by some sequence of functions which we know in a better way. Like for example, we will try to approximate a given function by simple functions or by continuous functions and so on. So we need to talk about limits and so on. And when we talk about limits, we need to understand that how things converge, what are the possible ways in for the convergence, and what can we expect for the limit of these functions under various kind of convergence. So this is what we are going to do. So okay, so definition is again put in the general setup. So you can consider a sequence of measurable functions, or rather this convergence can be defined for just for functions. You don't have to worry about whether they are measurable or not. So you have a set and you have a sequence of functions which are taking value in R or extended real numbers. Then we say that the sequence converges to of another function f in a pointwise sense. So this f is another function defined from x to R or the extended real numbers. So this is the pointwise convergence. So we say converges pointwise to f if at every point the sequence of numbers f and x converges to fx. So this f and x is a sequence of numbers. Okay, and you know what is the convergence for numbers. So that means you take any x and you take any epsilon positive, then you should be able to find an n, a natural number. This n may depend on x, correct? Because this is at that point we are talking about, such that the tail of this sequence, which is like f and x for n large enough. Okay, so that is where I am saying that n is bigger than equal to n. It gets closer to fx by this epsilon. So this is the usual definition of convergence for numbers. So once I evaluate fn's at the point x, this becomes a sequence of numbers. Okay, so basically we are saying that if this happens, then we say that the sequence fn converges to f pointwise. Okay, and now you see that if I have got a measure space, that means I have x and a sigma algebra on it and a measure defined on it, then I can also talk about this notion of pointwise convergence in the almost everywhere sense. Okay, so that means the convergence will happen at almost every point. Okay, so that leaves out this thing that there can be points where f and x does not converge to fx, but these points, if you collect all of them, they will be just a set of measure 0. Okay, so what does it say? That if you have a measure space, then fn is said to converge to f pointwise almost everywhere if the points at which the fnx does not converge to fx is of measure 0. On measure 0 sets we call them as null sets, correct? This is something which we had. So this is, so on a set of measure 0, you can afford to not have this pointwise convergence. Okay, so this is the idea. So sometimes there can be like points, or there can be a set of measure 0 where the sequence does not converge to fx, but that's okay. I mean, for all practical purposes that's going to be fine, because on a measure 0 set we are not really going to care much. Okay, for this course. So this is something you have to keep in mind. Okay, in fact, if you have a pointwise convergence almost everywhere on x, then what you can do is you can collect this set where this convergence does not happen, and since it is a measure 0 set, you can remove it from x. So you can call it x minus this null set. On that you will get pointwise convergence at every point, and that set has the full measure as the original set x. Okay, so this is something which we will and then the second property is the uniform convergence. This is very important and very nice. Okay, and here in the previous case the convergence was dependent on x. So basically now if we can get the convergence independent of the point that you want to start with, then that convergence is called uniform. Okay, now this definition and the previous definition of pointwise convergence, these are nothing new. You do them in your real analysis course. So I will just repeat. So we say that Fn, these guys converge to f uniformly if for every given epsilon you can choose an n. Okay, there is no dependence on the points, such that this is always less than epsilon for all n, no matter which x I choose. Okay, so this should happen for every possible point, or I mean there is a better way to write it, that the supremum over x of these differences remain less than epsilon. Okay, so this is something uh, you should you know I mean these things you already know, and this is well known, that uniform convergence, if uniform convergence happen, definitely the pointwise convergence happens, correct, because already you have chosen n and n. So but the converse is not true in general, and this is like one of the standard example you can write several examples, okay, where pointwise convergence happen, but I'm giving you this example, you should verify, and keep a scope of mistakes. There can be some small mistakes here, so you have to correct them if you find some. Okay, so for example, you consider this sequence fn x equal to x to the power n. This is a very nice, it's a polynomial function, it's a continuous function in particular, correct. So for every x in this closed interval 0 1, so if I take any fixed x to the power n is going to converge to 0 or 1, correct, because if x is smaller than 1, then raising powers higher and higher, you are going to make it smaller and smaller, so this will go to 0, but when x is equal to 1, it will converge to just 1, because this is going to be a constant sequence. So no matter which point I take, I can always find the limit, and hence the limiting function you can define it's going to be just finite value 0 or 1. So 0 when x is up all the way up to 1 from 0, and at x equal to 1, this is 1. Okay, so you see there are these important observations one should make, that even though we started with a polynomial, a nice function of a sequence of nice functions, but the resulting function has got a discontinuity, correct, because this is 0 and then suddenly 1. Okay, so each of these functions were very nice, but then the limiting function is not so good. Okay, but it's okay, it's not too bad as well in this particular example. Okay, so this is one example. I mean, if you have worked out your real analysis course, you must have seen these kind of examples, and also, like, a statement which I'm going to say, that with this you can easily verify that this fn's do not converge to f uniformly, because you can see that there is a problem at the limit, so uniform convergence is going to have a problem. And in fact, you might have seen this example, that the uniform limit of continuous functions is continuous. This is a theorem in your real analysis, so you can if you remember this theorem, you can directly apply, but I would recommend that you directly just use the definition and try to prove that fn's do not converge uniformly to f in this particular case, and try to think of couple of more examples, that will help. Okay, so the question is, okay, now in measure theory, this is going to be very important. The converse does not hold. Converse of the statement that pointwise convergence implies uniform convergence, this does not hold in general. So can we say something about it? Can we get a statement where pointwise convergence implies uniform convergence? So this is a major result, and it's called Egoroff's theorem. We will be using it, at a few places, and it's a very very beautiful theorem, and the proof is actually not so difficult. And what does it say? It says that if you are working with a measure space which is a finite measure space, that means the mu of x is finite, okay, and you have a sequence of measurable functions on this x such that they converge to f pointwise almost everywhere. Okay, so this is almost everywhere convergence. That means the points at which the convergence does not take place is it forms a null set. Okay, so in this setting, what you can actually guarantee, that you can get uniform convergence, but of course not on the full space, because we just saw an example. But what you can do is up to an epsilon you can do that. So that means if you take an epsilon positive, you can you will be able to find, so this theorem guarantees that you can find a measurable set. This E is in S, that means it is measurable, such that the complement of this set is very small. This is measure of this is less than epsilon, so that means this E is like almost full up to this epsilon. Okay, but you get that, on this E the convergence is uniform. So if you are allowed to leave out a small set, small is not a null set. Okay, this has measure less than epsilon, it doesn't mean that it is of measure 0. Okay, in fact that is not possible. Okay, so here we are saying that if we are allowed to leave a small measure set, then we can ensure uniform convergence. Okay, so this is such an important result. It tells you that pointwise convergence is going to give you uniform convergence, but of course you have to pay this small price, that you cannot do it on the whole space X. We just saw examples, but you will be able to do it like on most of the set, up to an epsilon you have to leave. Okay, so so this theorem, sometimes you will see the statement is actually written in this form, that the pointwise convergence is nearly or almost uniform convergence, okay, on finite measure space. So this nearly or almost is basically, this is the part, this epsilon part. Okay, it should not be thought of as measure 0 because that will be wrong. This is like you have to leave out a small epsilon, a set with whose measure can go up to that epsilon. Okay, so you give me an epsilon, then you should be able to, this theorem tells you that we will be able to find this E. So this E will depend on epsilon. Okay, so this you have to keep in mind. So if you change your epsilon, this E will also change. All right. So let us see how to prove it. So what we will do is, what is given to us is just this fact that Fn's converge to F pointwise almost everywhere. Okay, so out of this we have to sort of manufacture this set E, and in this process we are allowed to drop this set which has a measure at most epsilon. Okay, so this is how we will make use of this pointwise convergence and construct this set. Okay, and this is very easy. So first of all, as I told you when I introduced this notion of almost everywhere convergence, that without loss of generality you can assume that Fn's they converge to F pointwise for every x. How? Basically you look at the set where this convergence does not happen and remove it from X. Okay, so if I remove it from this thing from X, I still get a finite measure space with measure of this being same as the original mu of X. So I can call that X minus that null set as my new X. Okay, so that is what this statement is. And then okay, I have used here this epsilon tilde because in the statement there is an epsilon. And just write down the definition of pointwise convergence. So if you start with a point and an epsilon tilde, then this is something you have, correct, that you will be able to find an n such that the tail converges to Fx. This is what. So what we are going to do is this epsilon tilde, we are going to put here a sequence of numbers which goes to 0, and the convenient one is just take 1 upon n. Okay, so you take a pair of natural numbers. This n is going to refer to, in the 1 upon n sense, to epsilon, and then this k is going to be this capital N. Okay, so collect all these points x such that this happens, that fj x minus fx remains less than 1 upon x for all j bigger than k. Correct? So for every epsilon you can find this. So these sets will have lots of points. Correct? So now two things you can notice, that these sets, if I go from, so let us fix n, so that is your epsilon, okay, or epsilon tilde. So if I go from k to k plus 1, there is a containment between these sets. So for each fixed n, this ekn is actually contained in the ek plus 1n, because if this thing holds for k, this thing will also hold for k plus 1, because k plus 1 is larger than k, isn't it? So this is very easy to see. And so this is like an increasing nature, and actually this is going to increase to x. Why? Because we know that at every point x, I will be able to find such a k. So eventually you will get a whole of x, correct? Because we have pointwise convergence. So as k goes to infinity, because this is an increasing sequence, this we get that ekn for each fixed n, this converges to the whole space x. Okay, so basically now we will make use of those results which we had proved. Here we are actually going to make use of the result for this increasing sequence of measurable sets, and then connect to the measures for the general space. If you are not comfortable yet with the general space, then what you can do is you replace this x by a finite measure subset of the real line. Okay, so this will be a finite measure if you are not comfortable with general space x. Okay, so then if we know that measure of x is finite, and ek is there's a sequence which converges to x in the increasing manner, then I will be able to approximate the measure of x by these ekns, by taking this k very large. So that means if I look at the difference of x minus en and then k, so this k will be chosen. So here we are saying that we can choose, because n is fixed, so we choose this k and put a suffix n, because this will depend on n. So we choose n large enough such that this measure is small, correct? This can be done because these ekns, they converge to x, and x has got a finite measure, so you can write x as x minus ekn union en kn. Okay, so now this is going to be a disjoint pieces, and measure of e and k, this converges to x, so this is going to be like almost a measure of x, and hence the difference is going to be very small, correct? So this is something we can always do. And here this 1 upon 2 to the power n we are choosing because we have constructed a sequence ekn. So there will be we will have to take countable intersection and countable union. So we will have to take sums, and we want to make sure that the sums that when we take, they are finite. So that is why 1 upon 2 to the power n. Okay, now once I have done this, two things one has to keep in mind, that on these sets we have pointwise convergence, and this set is very close to x. So if I want to make sure that if I want to construct a set where you have uniform convergence, what will you do? Naturally you will take the intersection of all such possibilities, but you have to make sure that the part that you are taking the intersection, the total measure of the difference is small. Okay, so that we can make sure. How do we make sure? By just this, that this series 1 upon 2 to the power n, this is a convergent series, and hence what you can do is you can choose a large n such that the tail is smaller than epsilon. So this is the epsilon that is given in the statement. Okay, this is the same epsilon. So now what is the advantage of this? Now basically what we will do is we will look at these sets for n bigger than or equal to this and take their intersection, so that because we have a pointwise convergence, so when I take the intersection, this kn part is going to disappear, this dependence of this is going to disappear, and the resulting set, which we are calling as a epsilon here, we will have uniform convergence. Okay, so we will verify this. So notice two things. The first of all, what is the measure of the difference? Mu x minus a epsilon. So if you put it, so this x minus intersection of this, you can see that this is less than or equal to mu of x minus en kn, and then you sum over all these guys. Now we had chosen these guys in such a way that their measure is less than 1 upon 2 to the power n, and then this capital N was chosen so that this whole tail sum is less than this epsilon. Okay, so at least we know that the set which we have chosen, that a epsilon, has got measure less than epsilon. Okay, so now we claim that on this a epsilon the convergence is uniform, and in fact this is easy because it is chosen as the intersection of sets where you had the pointwise convergence. So here taking the intersection just to make sure that things happen for everything. That is the property of intersection, correct? So that will imply the uniform convergence. How? It's easy. So you can take a delta positive and then choose n larger than this capital N was fixed before. So choose an n such that 1 upon n is less than delta. Okay, and so this is the role of 1 upon n. This should be a sequence of numbers which is going to 0. Okay, that's all. So if I choose this, then by the definition of the set A epsilon, that if I take any point in A epsilon, then I am going to get that fjx minus fx is less than 1 upon n, and hence this is less than delta whenever j is bigger than k. So once I have this, you see that there is no dependence on the point x, and hence you get that the convergence is uniform on the set A epsilon. So you basically have found what is your E. Okay, so this E is nothing but the set A epsilon. Okay, so this is something very important, and all we have used as the pointwise convergence in a clever way. Okay, that's all. So if you read through this, you will understand it in a better way, and if there are confusions, we can discuss the proof again when we have our discussion session. All right, and then actually one can write down a slightly stronger statement of the Egoroff's theorem, namely that we can actually demand that this set E that we have chosen, this is a closed set. Okay, but this closed set you will be able to talk about when you know something about X. If X is just a set with no topology and so on, then this being closed and on doesn't make sense. So take for example the situation of Lebesgue measure. Okay, so then you take X to be a finite measure subset of R, and then on this you can talk about closed, open, all these things. So here actually we can say that there is a closed set E. So this is an additional property. So that means you can choose set E to be much nicer set, okay, with this property that measure of X minus E is small, and Fn's these guys converge to F uniformly on this E. Okay, and how do you do this? So basically, for this given epsilon, apply the previous part with epsilon by 2 and get a general measurable set with the measure of x minus epsilon by 2 less than epsilon by 2. So this a epsilon by 2 is just a measurable set. It need not be closed, but from here then we can use the property of measure, Lebesgue measure here, and choose inside this, because we had seen that the sets can be approximated by closed sets from inside. So you can choose a closed set E such that the difference of a epsilon by 2 and E is less than epsilon by 2, and then this E is going to do the job. This is closed, and this is the part which is not in E is at most of measure epsilon, and of course uniform convergence happens on E because this is just a subset. Okay, so this is like a corollary, but in particular cases this is also going to guarantee that you can actually choose the set E to be a closed set. Okay, so I will discuss some more results in this direction about convergence, and then we will discuss some situations where we can apply these results. We'll do it in the next class. All right, so see you.